ideal transformer. Transformer with no losses, a loss-free transformer, no iron losses, no copper losses. We have already discussed. Transformer works on the principle of electromagnetic induction. Let us consider a transformer having two coils, primary and secondary coil. Let N1 be the number of turns in the primary and N2 be the number of turns in the secondary. We have discussed that when you apply alternating voltage to the primary, current will flow through the primary winding. As circuit is closed, current would surely flow, which establishes a magnetic field in the core. And this magnetic field links both the windings, primary as well as secondary. As magnetic applied voltage was of alternating nature, magnetic field established would also be of alternating nature. Hence, as per Faraday's laws of electromagnetic induction, EMF will induce in the primary. As magnetic flux linking to the coil changes, hence EMF will induce in the coil, and this induced EMF is known as self-induced EMF. Likewise, same flux is also linking with the secondary winding, hence EMF will induce in the secondary winding. That V2 be the terminal voltage. As we have discussed that in case of ideal transformer, it is a loss-free transformer, that is no winding losses is there, no core losses are there. Means at no load, when you apply a voltage V1, magnetic flux phi is established. When you apply a voltage V1, current will flow to magnetize the core, and let this current be denoted by I. No iron loss is there, that's why the component of current, a small current which will establish the magnetic flux phi, is I. When magnetic flux linking with both the coil changes, hence EMF will induce in the primary as well as in the secondary. And direction of induced EMF, you are all aware about that, is given by Lenz's law. It will oppose the cause produced. It will oppose the V1. That's why we have indicated it in phase opposition. Now, and as this is a loss-free transformer, your applied voltage, no winding resistance we have considered, no winding losses, I square R losses, and V1 would be equal to E1, no magnetic leakage is there, and your V2 would be equal to E2. So this can be, you can represent a phasor diagram for the ideal transformer at no load. Whenever you connect the load, current will flow through the secondary winding, and input power would be equal to output power. V1, I1 would be equal to V2, I2. Or V2 by V1 is I1 by I2. That's why these transformers are being used in the transmission lines, so that we can reduce up the size of the cross-sectional area of the conductor. If your voltage level is increased, current level, they are inversely proportional. Voltage and currents are inversely proportional. Voltage is increased, current will reduce for same power. That's why we use its transformer to transmit it at high voltage. We use a step-up transformer, and so that the current would reduce up as you increase the voltage, and cross-sectional area of the conductor would be required less. For example, you think about if your requirement is 400 volt. If you generate 400 volt and transmit at 400 volt, you can imagine what would be the, whereas for example we are transmitting at 400 kV, means if we step up by thousands time, current will reduce up by 1000 times. You can roughly say size of the conductor is reduced by 1000 times. So you can imagine what would be your conductor size if you transmit the user level voltage. So that's why transformer becomes important. Now we were discussing the ideal transformer. So this would be, but in actual conditions, your ideal transformer is not feasible. But there is no possibility of having, because no device is a loss-free transformer. No magnetic material is a loss-free. No conductor, if you can say, which can be practically used in the application, is loss-free. That's why it is not viable to have a transformer, loss-free transformer. But we have started the what if the transformer is ideal, what would be the same? Your terminal voltage would be equal to the induced EMF. V1 would be equal to V2, E1 would be equal to E2, and this magnetizing current would be negligible, that is just to establish the magnetic field in the core. Let's move to the EMF equation of the transformer. What would be the equation for this induced EMF E1 and E2? Equation of transformer. Let us assume that N1 be the number of turns in the primary winding, N2 be the number of turns in the secondary winding. When you apply the alternating voltage V, it would establish a magnetic flux phi in the core. As the applied voltage is of alternating nature, your flux would also be of alternating nature. Let this be the flux. This will be the maximum flux in the positive direction, 0, pi, 2 pi. And phi is the maximum flux, and phi N1 be the number of turns in the primary, N2 be the number of turns in the secondary winding. Find the maximum flux in Webers and V into A, where AI be the cross-sectional area of this iron core, Bm be the magnetic field density. Now, what is the induced EMF? Is directly proportional to d phi by dt, rate of change of magnetic field. Time period for a cycle is t, and that is equal to 1 by f. Now your flux change is from phi maximum to minus phi maximum. in a time period of t by 2, this t by 2, or it changes from 0 to pi, 0 to phi m in a time period of t by 4. For example, let us consider your flux is changing from 0 to phi m in a time period of t by 4. So what would be the EMF induced? H, change of flux is phi m minus 0. Change in time is 0, t by 4. So t by 4 minus 0 is t by 4. Or t by 4 we can represent as 1 by 4 f. Or EMF induced is 1 by 4 f phi. So this is the induced EMF, average value of induced EMF. Value of EMF induced is 4f phi m. We know for sinusoidal wave, what is the form factor? RMS value by ratio of RMS value by average value. And for sinusoidal wave, it is 1.11. It is 1.11. What will be the RMS value of induced EMF? Induced EMF, as we have considered only one term, so it will be term. So this would be 1.11 1.11 into average value 4f phi m. Unit of this you can write it Weber second or volt. So this would be the 4.44 f phi m volt. So now EMF induced in the primary winding would be 4.44 N1 f phi m, or we can write it as 4.44 N1 f, you can write it as Bn AI volts. Similarly, EMF induced in the secondary winding 4.44 N2, number of turns in the secondary would be N2 f phi m, because the EMF is induced due to the mutual flux is same. Flux which is responsible to induce or which links with the both the windings is known as mutual flux. Here we have considered that there is no magnetic leakage. Flux which is linking with the primary and also linking with the secondary. .44 N2 F Bm AI. Now you can divide these. We will divide this. Your E2 by E1 becomes N2 by N1 and let it be K, turn ratio. Turn ratio of the transformer. Turn ratio of the transformer, ratio of the secondary turn to primary turn or secondary EMF to primary EMF is known as turn ratio. In case of ideal transformer, we have assumed or we know this V1 is equal to E1, V2 is equal to E2. So in case of ideal transformer, your E2 by E1, or we can say it V2 by V1. Keep in mind, this is only in the case of ideal transformer. When we have terminal voltage is equal to the induced EMF, N2 by N1 is K. So these are the equations, EMF equations of the transformer, and this will be the turn ratio of the transformer. Or we have already discussed in case of ideal transformer, your V2 by V1 is inversely proportional to I1 by I2 is equal to N2 by N1 HK. That is in case of ideal transformer. The current is inversely proportional to the voltage. Now we will start discussing actual transformer step by step. Transformer with your core losses and without magnetic leakage. Or actual transformer. So we will start transformer on no load. No load. Or transformer on no load. When your transformer is on no load is connected to the secondary winding. And we have considered that now losses are being considered in that transformer. Your winding, for example, your winding is having certain losses resistance, but there would be the I square R losses, and your transformer is having core. It would require certain additional current to supply its hysteresis and eddy current losses. So when we apply a voltage V1 on the primary side, but a flux would be established in the core, and your transformer will drive current of no load current, which will supply your winding loss, because secondary side is open, no secondary current is there, no secondary copper losses is there, only primary copper losses will, no load copper losses would be there, and it will supply the magnetizing component, or to magnetize the core of the transformer, and which would having an angle of 90 degree, and to supply the active component of the losses would be the that is your core lossage, having the hysteresis and eddy current lossage. As the current is low, your eddy current lossage might be lesser, and the main lossage and this resistance is generally winding resistance remains low. So your no load copper lossage would be negligible. So the main part here would be your hysteresis and eddy current lossage, or significant part would be the hysteresis loss, and your current would lag by an angle I naught, which is of two components, magnetizing component and another component is what? Active component, which is in phase, is active component, with the component which is in quadrature is the active component. So what will be the power at no load? It will be V1 I naught cos of phi naught. And what will be the current? Magnetizing current, no load current, sine of quadrature component, sine of phi naught, and Im, Iw, I naught cos of phi naught, and your I naught would be equal to the Im square plus Iw square, where phi naught is the angle between V1 and I naught, this voltage and this current. Now, when magnetic field is established, EMF will induce in primary, E2 will be induced in secondary. If you consider the winding, there is no magnetic leakage and the winding resistance is negligible, you can treat this E2 as E2. If the resistance is 0, considered to be 0, and the transformer is having no magnetic leakage. We will discuss later on what is the transformer on the level. Neglecting resistance of the winding and magnetic leakage. We have discussed the transformer on no load, and this no load current drum is to be utilized to magnetize or to establish the magnetic field in the core and to supply the lossage. So this component to supply the lossage, this is to establish the magnetic field in the core. Now, when load is connected, here in this initial case, we are assuming that the winding resistance is negligible and there is no magnetic leakage. Means flux which is linking to the primary is also linking to the secondary. When load is connected, but obvious current would flow through the secondary coil. When current flows through the secondary coil, your secondary magnetomotive force would be established, which would establish a flux phi 2 in opposite direction to the main flux. And there is current, there is magnetic field. When current flows in the secondary winding, there will be magnetic field due to that current. As this magnetomotive force establishes a flux phi 2 in opposite direction, that's why this magnetomotive force is also known as demagnetizing magnetomotive force. It will try to reduce this main flux. When this main flux reduces, this EMF will induced would also reduce. And this EMF induced is equal to this applied voltage. As we have neglected the resistances and magnetic leakage, so we have assumed that your E2 is V2. As your source dominates in the circuit, it will draw an additional current in the line, so that the demagnetizing effect due to this secondary magnetic force can be neutralized. So it will develop an magnetic force, additional magnetic force. Primary will develop an additional magnetic force, that is your N1 I1 dash. Let this be phi 1. Develop an additional magnetic force which develops a flux to neutralize the secondary flux or flux developed by the secondary magnetic force N2 I2, or flux developed by this demagnetizing ampere turn. Means this phi 1 dash would be equal to phi 2, so that your main flux would sustain and it would not change. If there is change, that change would be negligible, or that would remain more or less same. Now, the load may be resistive, inductive or capacitive. The phase angle between your V2 and I2 would depend upon the nature of the load. If the load is pure resistive, phase angle between voltage and current would be 0, secondary voltage and secondary current. If the load is inductive, your I2 would lag this secondary voltage V2 by phase angle of phi 2. If load is capacitive, it will lead by phase angle of phi 2. Accordingly, your phasor diagram would change. So first, draw the phasor diagram for no load conditions. We have already drawn this phasor diagram. Now, we have assumed that your V2 and E2 are same, because we have neglected your resistances and magnetic leakage. We are not considering it at this initial stage. If the load is pure resistive, for example, load is pure resistive, your secondary current and your terminal voltage will be same. We have represented it. Both are in same phase. Due to this current, and current would be in, now remove this, a counterbalancing current which would be in phase opposition to the I2. Your primary current would be phasor sum of I0 and I1 dash, and it will make a phi angle with phi. You see, phi 2 is 0, but we still have the angle. Counterbalancing angle would be same. Your V1 and I1 dash and V2 and I2 would be same, but phi 1 and phi 2 would be different. Now, in case of inductive load, draw again. First draw for no load. V1, E1, E2, and E2 is V2. V1 is equal to E1. Let this be the I node, and this be the phi node. Now, your load is inductive. Your current I2 lags V2 by phase angle of phi. Let this be the I2. This angle be phi 2. I1 dash would be represented in phasor position of this phi 2, means this phi angle between V1 I1 dash would be equal to phi 2, and this current I1 would be the phasor sum of I0 and I1 dash, and this angle would be phi 1 between I1 and V1. So this will be the phasor diagram for inductive load. In case of load is capacitive, V1, E1, E2, V2, I0. Again draw the first draw for no load. Then this is phi naught. Now your current leads the voltage. Let your secondary current leads this V2 by an angle of phi 2. Phi 1 dash this is resultant current, and this will be phi 1. So this would be the phasor diagram if the load is capacitive. From here means this N2 would be equal to N1 I1 dash, or your transformation ratio N2 by N1 would be equal to I1 dash by I2 is equal to K, and K is the transformation ratio or time ratio of the transformer. Or E2 by E1 is equal to N2 by N1 is equal to I1 dash by I2 is equal to K. Means we have now, in place of this current I1, we have the current I1 dash, counterbalancing current. Or we can write it as V2 by V1, because we have neglected the resistances and magnetic leakage. So this E2 would be equal to V2 and E1 would be equal to V1.